Assalamualaikum. Salam sejahtera to all. Hi, we meet again in part 2. So I will proceed with principle of superposition until standing wave resonance. Okay, so principle of superposition. The definition is if two or more traveling waves are moving through a medium, the resultant wave function at any point is the algebraic sum of the wave function of the individual wave, as you can see in the figure. Here, this one is represented by D1 and this one is represented by D2, and the sum is, this is the wave number 3, D3, and this is the sum of all three, so equal to T1 plus T2 plus T3 in terms of X and T. X is displacement, T is a time. Let's have a look at the reflection and transmission. A pulse or a wave undergoes various changes when the medium it travels changes, as you can see in part A and part B. It's depending on how rigid the support is. Two radically different reflection patterns can be observed. For example, in A, as you can see, N1, the support is rigidly fixed. So the reflected pulse will be inverted to the original due to the force exerted on the string by the support in the reaction to the force on the support due to the pulse on the string. Okay, inverted and reflect back to the origin due to the original force exerted. As you can see here, it's reflect back. Okay, in part A. If let's say the support is freely moving, okay, not rigid here, okay, then the reflected pulse will maintain the original shape. As you can see, this is the first one, then after and here, so it will continue in the original shape here, but moving in the reverse direction. So can you see the difference between these two, class? Alright, so it depends on the support, that is transmission. So different media, transmission through different media. As you can see in the figure, different media means when a pulse or wave travel from one medium to another medium, as you can see from the light section in part A to a heavy section, okay, different medium, part of the pulse will reflect and others undergoes transmission, as in figure B. Because of different media, so part of them will reflect and part of them will transmit, passing through the boundary and propagating in the new medium. So we can conclude that when a wave pulse travel from medium A to B, light section or heavy section, VA is greater than VB, then the pulse is inverted upon reflection. If let's say VA is less than VB, the pulse will not inverted upon reflection. For boundary condition, as you can see in the figure, the medium is different. One is light section, the second one is heavy section. When two medium occur, so half of them will reflect and half of them will transmit, as I mentioned earlier. When a wave encounter a denser medium, boundary condition means that end here, after it reach end here, it will transmit and it will reflect. Okay, so when a wave encounter a denser medium, the wave will be partly reflected and partly transmitted, the same as previous lecture. If the wave is speed, same as previous slide, if the wave speed is less in the denser medium, the wavelength will be shorter. Okay, please remember the hint here. For a 2 or 3D wave, For example, a water wave can be represented by wavefront. Wavefront, as you can see, this is a wavefront, which are curve or surface where all waves have the same pace. That is the mean by wavefront. A line drawn in the direction of the motion and perpendicular to the wavefront is called a ray. This is called as the line drawn in the direction of the motion, follow the motion, and perpendicular to the wavefront we call as a ray. So wavefront far from the source. When the wavefront is far from the source, this is, for example, this is our source. Okay, then it's become far away and have lost all their curvature and are nearly straight. As you can see, when the source are far away, when the wave are far away from the source, they become straight. For example, ocean wave, and we also call as plane wave, as in the figure B. For a reflection, still remember we have learned in chapter 1 the condition of reflection. For of a 2 or 3D plane with the angle that incoming or incident wave that makes with the reflecting surface is equal to the angle that met by the reflected wave, because it's happened in one medium. This law called the law of reflection, where the angle of incident theta I equal to the angle of reflection. As you can see here, the angle here is same to the reflection, is same to the reflected wave. Okay, this is a wavefront, this is a reflected wavefront, same. The angle of incident is the angle between the incident ray and perpendicular to the line to the reflecting surface, to the reflecting surface. The angle of reflection is the angle between the reflected ray and perpendicular line to the reflecting surface. Interference. Have you ever seen this kind of situation? Alright, what you can see from the figure? Okay, another example. Okay, as you can see in the figure here, there are crests, there are crests, and they are throw here. Whenever a crest go inside with a throw, okay, here on the horizontal line here, the water surface is flattened. Okay, as you can see, the flattened part is when a crest met with throw. Double crest here. Okay, as you can see, the white color, all the white color here. Okay, double crest here. What is when a crest coincident with crest? Okay, crest coincide with a crest, so that is why it will become double crest. Flatten region, okay, flatten region here, 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 and here. A crest coincide with a throw. Okay, understand, class? There are two types of interference, whether it double crest or it will flatten, or it will become a double crest. Okay, as I mentioned, there are two types of interference based on the figure previously. Okay, when two waves pass through the same region of space, they will interfere. Interference may be either constructive or destructive. Okay, A represent a destructive, B represent constructive. This one, when a crest met with a throw, so it will become destructive interference. This one, when a crest met with crest, so it will become double crest. The two wave is set in pace when the constructive interference occurs, or when the crest of the first wave repeatedly made the crest of the other waves, as you can see in the figure. Crest made with crest. So some of the wave they will add constructively, as in last figure here. And the pace is said out of pace when destructive interference occurs. For example, when a crest meet with throw and we plus all together, then they will add destructively, means that flattened surface will occurs here. And as in part C, shows that when the crest meet with half crest, so they will act partially destructively, or we call as intermediate C. Constructive interference means that the amplitude increase when the wave meet, as you can see here. The amplitude are increased. Destructive interference means that the amplitude decrease when the wave meet. Okay, we add both them, so they will decrease. This one for partial or intermediate wave. Standing wave or resonant, that is the next subtopic. If two sinusoidal wave with the same amplitude and wavelength travel but in the opposite direction, as you can see in the figure, in part A it moves to the left, part B they move in to the right. So the interference with each other will produce a standing wave, as you can see in part C. This is we call as standing wave. Okay, each point represent node and antinode, and I will show the detail by the next slide. It will difference by the time, as you can see, for time equal to 0, this is standing wave, and by the time 1/4 period, okay, this one means that when the crest meet with throw, so it will flatten. Okay, the standing wave will flatten. The third one, when a crest meet with a crest, with throw meet with a throw, so it will produce, as you can see in the figure here, two wave traveling with same amplitude but different opposite direction, with different direction, so it will produce that. So standing wave have node and antinode, as you can see in the figure. This one is node, this one is antinode. Okay, a node is a point where the string stay at its equilibrium position. This is known as equilibrium position. Antinode is point where the wave is as far as it gets from the equilibrium, far from equilibrium. This is a antinode. Standing wave occurs when both ends of a string are fixed. As you can see, fixed. In that case, only waves which are motionless at the end, means that at the end here are motionless, the string can persist. They are not where the amplitude is always 0, and antinode where the amplitude varies from 0 to maximum value here. So this is fixed at that equal to 0. So this is general equation of the standing wave. How we get this equation? Then later we derive. I'll show you how to get this equation later. The distance between adjacent and antinode is equal to pi over 2. Distance between adjacent antinode. Okay, antinode is pi over 2. Alright, then the distance between adjacent node is equal to pi over 2. And the adjacent node and the distance between a node and adjacent antinode is equal to pi over 4. We plus both together, so we got pi over 4. Formation of standing wave. Okay, you can see the detail here, how the standing wave form. Right? With different periods, so different standing wave form. Not anti-knot, not anti-knot. This is standing. So let's have a look at the mathematical representation of standing wave. For standing wave, we need to consider two traveling waves moving in opposite direction on a string. Let's take y1 as wave number 1 in terms of xt, a sine kx minus omega t, and the second one y2 in terms of x and t as a function x and t. X is a distance, t is a time. A sine kx plus omega t. Y here is negative, here is positive. We need to consider both because in the opposite direction, one to the left, one to the right. So we add both equation, y1 plus y2, a sine kx minus omega t plus va sine kx plus omega t. Then from the cosine rule or trigonometric function, okay, check back the formula. Sine 1 plus with sine 2, so we'll get this equation. Okay, I will not show you the detail, okay, because we just simplify the equation. So we got this equation, okay, when sine 1 plus sine 2 equal to 2 sine half omega 1, sorry, theta 1 plus theta 2. So it's here, it will become cos half theta 1 minus with theta 2. So simplify, we will get y1 in terms of x and t equal to 2a. 2a is a amplitude sine kx cos omega t. So this is the general information for standing wave. Right? Then at for a standing wave y x t equal to 0. So y here equal to 0 at x equal to 0 and x equal to L. Then satisfy when sin KL equal to 0, given that KL equal to pi, 2 pi, 3 pi until n pi. Since we know that k equal to 2 pi over lambda, so then lambda from the previous chapter, we know that lambda n equal to 2L divided by n, which is n is the integer 1, 2, and 3, and so on. So remember, this is the equation of standing wave. So the wavelength 2L divided by n, or from here we can find the L as well. Just rearrange the equation. L equal to n lambda divided by the 2 from this equation here. So we just simplify the equation. So then frequencies, unit is still same. Lambda is meter. Frequencies Fn in terms of n integer, n 1, 2, 3. Then substitute the equation from the width to f lambda. If let's say we want to find the f, rearrange the equation. So we arrange the equation. So we divide by lambda n equal to 1, 2, 3, and v per 2L equal to n f1 and so on. So the frequency of the standing wave on a particular string are called natural or resonant. Spring or pendulum has only one resonant frequency, but a string may have infinite number of resonant frequency. Okay, remember, pendulum only have one resonant frequency. These frequencies are also referred to as the fundamental and harmonies, as you can see in the figure. This is the length in figure A. Then after the wave start to vibrate, so then it will produce knot and anti-knot here and knot here. And this we call as fundamental or first harmonic, known as labeled as F1. And again, it will vibrate again, produce two wave. We call as first overtone or second harmonic, F2, which is F2 equal to 2 F1, 2 times F1. And second overtone or third harmonic, F3, third harmonic. Okay, so this is a vibrating one. So you can see here, Standing wave are set up in a string when one end is connected to a vibrating plate to produce a standing wave. When the plate vibrates at one of the natural frequencies or resonance of the string, large amplitude standing wave are created. This is large amplitude. Large amplitude here. Okay, large amplitude known as antenna. Alright. Standing wave pattern in a vibrating water glass, as you can see in the figure A. The glass shattered if the amplitude of vibration becomes too great, as you can see in the figure P. A water glass shattered by the amplified sound of a human voice. Let's try example. Two waves traveling in opposite direction on a string fixed at x equal to 0. Highlight the information given. X equal to 0 produce a standing wave. Remember, standing wave described by the function y1 and y2. There are two equations because this is standing wave. 0.2 sine 2.0x minus 4.0t meter. And this one same but difference in sign only because this is opposite direction. So we have a negative and positive. First one, A, determine the function for the standing wave. So the question asks for the function. Recall back from the slide general equation for the standing wave, which is y equal to 2a sine kx cos omega t. Right, let's have a look at the solution. For that, we proceed with B first. What is the maximum amplitude at x equal to 0.45? C, what is the maximum amplitude and where does it occur? A, okay, as I mentioned, we took this equation and substitute all the information given from the question. Substitute all in the equation. Therefore, y equal to 0.4, 2 times with 0.2, so we got 0.4 here, sine 2.0, because k is 2.0, x cos 4.0 is the omega here, time with t. Okay, so we got the wave function for standing wave. Then B, the question asks for the maximum amplitude when x equal to 0.45 meter. So we just substitute the value of x in the equation here from part A, 0.4, so 0.45 times with 2 here, so we got 0.9 cos 4.0 times. So calculate all this of the information here. So we got 0.31 for amplitude cos 4.0 t. So t is not changing because for the maximum amplitude occur. So then when cosine, so when maximum amplitude is 0.4 meter, the maximum amplitude is 0. We find part A. And when sine equal to 1 and cosine equal to 1. So actually maximum amplitude occurs midway between nodes. Alright. First node must start at 0 because node is at 0, which is at equilibrium. Second node is at x equal to lambda over 2. Lambda over 2 means that from adjacent, between adjacent and the node. So that's why we got lambda. So 2 pi divided by 2k, 2 pi divided by 4. So then nodes x equal to lambda equal to 1.57 meter. Therefore, for antinode occurs at x equal to lambda over 4 because we take midway. So then substitute the equation, substitute lambda in here, so we got the value is 0.79 meter. Lambda is 0.58. So note that here note occurs every 1.57 meter from here if the string is long. Let's try another exercise. Right, a standing wave YT is the total of standing wave is produced by the interference of two identical waves. Identicals means that the amplitude same, the wave constant is k is same, and the omega also same. This means that by the identical, just the direction is different, which is represented by y1 and y2, moving along a string in opposite direction. That is the difference between these two waves. The only difference is opposite direction. So the amplitude of standing wave is 20 centimeter. Adjacent antenna are 30 centimeter apart. The frequency of the wave is 40 Hz. The frequency here given to find the omega, because in the equation we have omega t and kx, right? So you need to find the omega by using this equation. Okay. Substitute the frequency given in the equation here, 2 pi f. So then compose suitable wave function for this y1 and y2 which may produce standing wave measure. This is total, and the amplitude already given 20 cm. The frequency we can find, and the adjacent antenna here we can find the value of k from here. Okay, refer notes back. Okay, let's try to solve by your own. Try to solve. I already give all hint. Then you just find the k, so substitute in the general equation of wave function y1, what is y1, y2, what is y2. So this is the question asked for. Then y1a sine kx cos omega t. A given already, sine constant, kx, k find from here. Omega is given frequency here, so you can find omega. So a, k and omega is same. The difference is only the direction. So this you can find what is y1 and y2. Then show the equation here. Okay, very that's simple. All for chapter 3. So thank you for listening to me, and have a nice day. If let's say you have any inquiries related to the chapter, you can ask in the medium that given by your lecturers. Thanks again. Bye bye.